Hi everyone, welcome to GeoStat. My name is Dipankar Bera. Today I am going to discuss principal component analysis, the main concept behind the principal component analysis, and additionally I will explain why we use principal component analysis, including its benefits and real world applications. In this video, I will not go into the mathematical calculations or derivations. I will just provide detailed understanding of principal component analysis, why we use it, and its real-world applications with examples. So PCA stands for Principal Component Analysis, which means we analyze the principal components of dataset to understand its underlying information. This information includes patterns, trends, distributions, and the significance of the data. As an example, you can see the principal components of a random dataset here. Principal component 1, principal component 2, and principal component 3. But before performing an analysis, we first need to know what principal components are. Actually, principal components are extracted data from the large datasets using some mathematical calculations. Principal components transform a large set of correlated, noisy, and often uninterpretable variables into a smaller set of uncorrelated informative variables. You can call it a dimension reduction or feature extraction techniques, because you can see here the original dataset has 9 dimensions. Dimension 1, 2, 3, 4, 5, 6, 7, 8 and 9. These are the factors of rice production of an area. Now we have reduced them to 3 dimensions. Dimension 1, 2 and 3. So a dimension reduction. We can also say that these are features or variables. So variables 1, 2, 3 to 9. And the data under each principal component are not directly taken from the original features. These are extracted from original features using some mathematical techniques. So, new data are developed that are extracted from the original dataset and contain the information of the large dataset in a smaller set of data. That means these dataset contain information of original datasets. That's why it is called feature extraction, not feature selection. Feature selection involves choosing the most important features from the large dataset, such as selecting 3 important features or factors out of 10 or 20 features. For example, I have selected here 5 key factors from a total of 9 factors using some mathematics. So these are 5 selected factors out of 9 factors of rice production. So here we are missing the information from the remaining unselected factors, specifically nitrogen, potassium, temperature, and irrigation. However, in the case of extraction, a new set of features is developed that retains the information from all 9 original features. Therefore, there is no loss of information. Now, question is that why we called it principal components? The term principal means importance or priority. The extracted components are the most important or dominant directions in the data that captures the largest possible variance or spread, where most of the information is stored. The word component refers to an individual part of a larger whole. Each principal component is a part of whole original variables that represents a combination of the original variables. A total of all components represents whole variables or original data. Thus, the first principal component captures the most information, followed by the second principal component, which stores the second most information and is uncorrelated with the first. Each subsequent principal component captures a progressively smaller amount of variance or information and remain uncorrelated with the all previous components. Check out this graph. Variance explained or information stored by each principal component, and cumulative line graph, and information shared by principal component 1 is greater than the principal component 2, principal component 3, principal component 4, and principal component 5. and sum of the all principal components represent the total variance or information of the original data. Let's assume we have two features, that means two dimensions of the dataset, and we develop two principal components. You can see here two principal components. In the direction of principal component 1, most of the variance or information is stored compared to principal component 2. These principal components are orthogonal, that means they are uncorrelated to each other. And sum of PCA 1 and PCA 2 is the total variance or information of the dataset. Let's discuss the purpose of extracting principal components from the larger dataset and the benefits we gain by doing this. The first point is that dimension reduction. It helps to reduce the number of dimensions in the data. When we have large datasets, they often contain noise, correlated features, that means dimensions with the similar information, which increase the data volume. Simply, larger dataset means larger volume, but principal components analysis helps to reduce this by transforming into smaller, uncorrelated and more informative datasets. So it removes noise, redundant information from the larger dataset by transforming it into a smaller set of data. So it reduces the dataset size, that means data compression. Check out this dataset. This original dataset represents the factors of forest carbon stock with 7 dimensions or 7 factors. By extracting principal components, I developed two principal components that retain almost 97% information from the original datasets. So this process removes noisy data and reduces the data size. Now let's look at this image. It shows the integer 2 and its corresponding pixel values. It has 10 dimensions. Purple color pixels represented as a 1 and the black pixels as a 0. As you can see, the left and right columns contains 0 pixel values along with some other pixels. If we remove this 0 pixel value, it would not affect on the shape of the digit 2. If we remove the leftmost and rightmost columns, it is a form of dimension reduction. This reduction helps to remove noisy and less significant data, therefore reducing the size of the image. Let's check out this image. It still represents the integer 2 even after removing the 0 value and 2 dimensions. This demonstrates noise removal or dimension reduction. Principal components works in this way. This picture shows the integer 2 using the 2 principal components. This is using 3 principal components. So we are obtaining almost same information using only 3 dimensions instead of original 10 dimensions. Check out this image. The original image has 500 into 500 into 3 pixels. 500 by 500 pixels multiplied by 3 because it contains 3 bands, red, green and blue. The PCA versions use 40 principal components and retain approximately 94% of the original information. You can see the graph here. Variance explained by each principal component. Check this PCA with 20 principal components and retain approximately 86% of the original dataset. The second benefit of the principal components is visualization. When we dealing with the large datasets, it becomes very difficult to visualize and identify the patterns, trends. For example, if you look at this standard living dataset from many countries, it is hard to make sense of it. Even we can't effectively visualize this dataset because we can't visualize beyond the 3 dimensions. This is the 2D plot and this is a 3D plot, but we can't go behind this. But after extracting 2 principal components that capture the majority of the information from all dimensions, we can visualize and understand the underlying patterns through a 2D plot. Check out this 2 principal components plot. Now we can visualize the data. We can see the Nigeria is quite far from the other countries and the rest of the country forming 2 distinct groups. Feature extraction. PCA helps to extract important new features from the large dataset. For example, we want to understand the influence of these factors on carbon stock, and these factors may be correlated to each other, which can affect on the accuracy of the model. Therefore, we can extract new features from these datasets that are uncorrelated and still retain most of the information from the original 7 explanatory factors. Check out this graph. It shows the variance explained by each principal components. The first 2 principal components explain nearly 97% of original data. That means the first 2 principal components store 97% information of original data. So these 2 principal components are newly extracted data to explain carbon stock. Improve model performance, handling overfitting, multicollinearity. As we already discussed, there is always multicollinearity in the large dataset, meaning the variables are correlated to each other. It can negatively affect on the model. And by extracting new features using principal component, we can get uncorrelated new features. As principal components are uncorrelated to each other, they handle multicollinearity. Also, when there is a large amount of datasets, there is always risk of overfitting the model. This means model may perform well during the training but fail to generalize to real world or test dataset. This often happens due to the noise outlier in the datasets. After extraction new features using principal components, we retain only the essential informations, which helps reduce overfittings and improve model performance. Now, let's move on to the applications of principal component analysis. This is the analysis of principal components. That means principal component analysis. I will discuss now how these components help us in real-world data analysis. First point is outlier removal. Abnormalities and anomalies are closely related terms that refer to the data points that deviate from the central position of the dataset. Principal component analysis helps in identifying the outliers, basically those points significantly deviate from the main structure of the data. Check out this principal components plot of living standards. So here, living standard of Nigeria is significantly different from the rest of the countries. It is far from the center of the dataset. PCA also helps in clustering or segmentation of the datasets. If you look at the living standard dataset, it is difficult to tell which group of countries are similar type of living standard. But check this living standard PCA plot. The data point can be grouped into 3 distinct clusters based on their position in the PCA space. So these countries form one group with similar level of living standard, and this is another group, and Nigeria is far away from the rest of the countries. Another example is that you can see here the rainfall data of 10 cities in 10 different locations. Here we want to identify the cities with similar rainfall patterns. Let's check out this PCA plot, basically PCA 1 and PCA 2 plot. You can clearly see here 4 distinct groups of cities. Regression analysis. Another real-world application is regression analysis. For example, we want to perform regression to estimate the carbon stock using these 7 factors of carbon stock. However, these factors might be correlated to each other that can affect on the accuracy of the model. To address this, we can extract new features from original dataset that are uncorrelated and yet retain most of the information from the original 7 variables. This process is known as principal component regression. Basically, when we use the extracted new features for regression analysis, we call it principal component regression. Check these extracted principal components from the 7 factors of carbon stock. Principal component 1 and principal component 2. These 2 principal components retain 97% of the information from the original dataset. So we can use these components to perform regression for estimating carbon stock. For predictions and machine learning models, we can use principal components for regression or other machine learning methods for prediction. However, I highlighted the regression analysis separately because when principal components are specifically used in regression, the approach is known as principal component regression. However, the extracted features can be used for any suitable machine learning models such as random forest, boosted regression tree, and others. For example, in land use land cover classifications, crop classifications, or any other type of classification task, we can use principal components. For example, when there are multiple satellite bands, we can extract the most important features from the all bands. These important features are then used for classifications rather than using the all bands. This approach helps in running the model with the better accuracy and speeding up the processing time by using fewer features. For example, suppose we have 100 bands with each band 1000 of pixels in an area. So data structure is here. So 100 bands corresponding to the 100 dimensions. But by applying principal component analysis, we can reduce them into fewer dimensions, which reduce the data size, so reduce the burden on our PC and speeds up the modeling. Here, I extract 3 principal components from 100 bands, which together capture 96% of the original data. Trend analysis. By analyzing principal components, we can understand the trends of the dataset over the time period. Let's check out the rainfall data of 10 countries. We want to understand the overall trends in rainfall over the time. Some countries might experience a decreasing trend and other might experience increasing trends. Our main focus is to identify the overall trends of rainfall across all countries. From a large dataset like this, it is hard to visually identify the trends, and plotting individual graphs for each country is also challenging. So we can use the principal components to quantify the trends. So extracted these 2 principal components explains almost 75% of the variance in the datasets. Now we can plot these 2 principal components and add trend lines. Check out the plot of the 2 principal components. It shows the overall trend in rainfall is decreasing. Another example is that we want to check the trends in the growth of economy of a country. We have some common parameters of economy like GDP, inflation rate, employment rate, interest rate, consumer confidence index, industrial production index. We generally consider that if GDP is increasing, the economy is boosting, but there are many other parameters to consider as well. These parameters can individually increase or decrease. For example, GDP may decrease while the employment rate increase. But to understand overall economic growth, we need to perform a PCA. Now check this graph. This PCA1 explains 90% of the original data and shows an increasing trend, indicating that overall economic growth is rising. So these are all for today. In the next video, I will discuss how PCA works and how to extract principal components from the original datasets. Thank you.